Hello everyone, I hope you are doing well. I am Dr. Adnan Ali Khan. As I told you that today we will start the tutorial lectures from the catalysis session. This session will be fully focused on catalysis, where we will discuss a single atom catalyst for the catalytic N2 reduction and for carbon monoxide oxidation. This paper is mainly focused on the N2O reduction, and this is our own paper published in Journal of Molecular Graphics and Modeling in 2022. Actually, in this paper, we select a graphene-like sheet which is based on boron and nitrogen, and then we dope this system with silicon atom and explore its catalytic activity for the N2O reduction. So, this paper will be completed in 3 to 4 different videos. In the initial lecture, we will show that how we will create a bare supercell of boron nitrogen graphene like sheet, and then how we will interact the N2O gas with the bare system, and then we will discuss different electronic properties of this system. So we will try to prove that a bare system cannot easily reduce the N2O. So then we will move to the silicon dope system, and after that we will show that how a single silicon dope system can easily dissociate the N2O gas molecule. I will use the Material Studio software. Initially we will perform different tutorials on Material Studio. After that we will move to other codes like Gaussian, WASP, etc. So our mainly focus in this video will be on Material Studio, and we will be use a DMOL code in Material Studio. So a little bit I am explaining that this is a graphical interface of Material Studio, where different codes are implemented in this Material Studio. Is these here we can easily see different types of codes are implemented in this Material Studio software. So in our first lectures we will mainly focus on DMOL code, and then we will move to CASTIF and Foresight, and after that we will discuss other different types of codes. But for catalytic study, the most easy and the best code is the Material Studio and DMOL system. You can I am showing different sort of simulations for catalytic reduction of N2. You can easily perform such type of simulation in CASTIF code also. The same procedure you can use. There are some little differences in CASTIF and Material Studio. In previous in the upcoming lectures we will discuss these things, that how these two are different from each other. So this is here, this is a main window where we will create a new page, and we will construct different structures here. This portion shows a library, backup files, different type of files which we are going to compute will be stored here. And for each file, you people can easily generate a separate folder and save each simulation in that particular folder with particular name. So initially you can generate a new 3D atomistic page. So click here. This is a 3D atomistic empty page. Mostly in articles we are using white color, so my background is white. You can easily change this from right click and go to display option, and then select background. In background you can choose any color you want to be displayed on your, which are shown by in your display. So you can easily choose a different type of color. I am basically using white color. Right click display option, so I am selecting white color for my simulations. This is our monolayer 2x2 supercell of boron nitrogen graphene like sheet. we will use this structure as a catalyst for our as a catalyst for into reduction. You can see this from different perspective, from different views. It can be easily moved, or you can easily rotate it by clicking on the right button of your trackpad or mouse, so you can easily view this structure from different perspective. So how to build this 2x2 super cell? For this you will need a unit cell. You can easily download this unit cell from anywhere from internet. You can easily take the latest constant, latest parameter from different already published papers. So this is a unit cell of 2x2 monolayer. So it is necessary that before constructing a supercell, you will initially optimize the unit cell of this structure. So go to demol code. You can easily select demol from this place. Also you can easily go to models and then select demol, and after that click calculations. So this is the input parameters. We are going initially to optimize the unit cell, so task will be geometry optimization, and more you will select 999 cycles. Different structures have different cycles. Some structures can easily be optimized in 2 or 3 cycles. Some can be easily optimized up to 100, 200. So we will select a maximum number of cycle. So the cycles will iteration will be 999, and here the quality will be fine. So note that these parameters will be constant. You will always be use these parameters for such type of simulation. We will discuss after that how and why we will change these parameters, why we will be use different other type functional like hybrid functional, etc. So initially we will use simple functional GGA, and will be use PBE functional. And here you will select Agrimi dispersion correction for the van der Waal correction. We will discuss this later, that what is mean by this. And you can for monolayers planar structure you can use symmetry, but some structures have distorted symmetry, so then you will not use symmetry. I am also not selecting this. Then select electronic. These all will be fine. Select a basis set all electron core treatment, and use basis set DNP, and then apply energy cutoff of 3.5. After that select more and change this value to 5, and so here you change the maximum cycle up to 999. Use smearing option. Cap points will be, you can use 2x2, 3x3, 4 depending on your computer power. So if you have a powerful computer, then you can use maximum number of K points. As we know that then is the number of K points will be more, so the accuracy will be more. Here I'm using just 2x2, that we can easily simulate the system. Orbital cutoff will be changed to custom, and the value will be 4.6 assign. After that close, and these are different properties. We will compute this after optimization. Just with optimization only select population analysis. This will show us different harsh field charges, surface charges of different atom. Go to JAV control and put the name of your simulation here. I'm going to I'm giving name unit cell dash OPT. OPT means that I'm going to optimize this cell. Select number of processors. You can choose different number of processors depending on your computer, that how much processors are there in your computer. And always select even number of processors, never use odd number. I'm selecting 6, and I am selecting 6000 or 6 GB RAM for this simulation. After that click on run. your simulation will be started. Here this is starting, and soon it will be changed to running mode. Close this input geometry. After running mode, you will see the this you will see different sort of files. This will be the output geometry which are going to optimize. As we seen that the optimization is successfully completed when the geometry optimized successfully. They will show you and they will show you that the optimization is successfully completed. So close this, also close all these files. And now I'm going to construct a 2x2 supercell from this unit cell. So I will be select the optimize. So here are different, you can see different files in the folder. So this one, this symbol will represent the final geometry optimize. This will show the unoptimized geometry. This will show the input file, different parameter which we were applied during the simulation. So these are here in input format. This is the window from where you can choose different options for simulations. This is job stated during the running. It shows you different energy convergence, different K points, different cycles. And this is the output file. This file is very necessary, so we will take different values from this file. After that, we will show you that I will show you that how can we select different values from this system. So I'm going to close this one. This is the optimized geometry, so you people can easily copy this unit cell to a new file. So right click, copy, and select a new folder. Click on the project name and create a new folder. I'm giving this system a supercell 2x2 new. So I already optimized the structure, so I'm giving this a new. Then select this folder and generate a new 3D atomistic file, and right click and paste. After that, close the unit cell, and I'm going to close this folder. Go to build, symmetry, supercell, and construct 2x2 supercell. This is a supercell. You can also generate this from right click, and then latest parameters. From this you can also generate the structures. These are the optimized parameter of this supercell. So this is our supercell. So we already optimized the unit cell of this system, so there is no need to optimize the whole supercell. This shows a vacuum of 20 angston. You can this change from here, crystal, rebuild crystal, and these are the latest parameters, different latest parameters. So you can change this from a vacuum from here. We are mostly selecting a 20 angston vacuum, which are more accurate for to reduce the interlayer interactions. So this is our supercell. There is no need to optimize this because we are already optimized the latest parameter of this unit cell. So we will compute a single point energy for this, and will compute different electronic properties for the system. So select here energy and go to electronic. All our things will be all the different parameter which we were set before. So we will select all those parameters. There is no need to change any sort of parameter. So go to directly properties, select band structure, the quality K points will be fine. generate a path for these key points, and after that select density of state. You can also select calculate partial density of states. So partial density of states is necessary during the simulations of interaction of different analyte with the surface. You can also select here calculate partial density of state, then select electron density, deformation density, select electrostatic. So we will just compute the electrostatic potential, and after that we will select population analysis. We almost already computed the population analysis, but per the whole supercell you can also compute this. So leave all these properties. We will discuss these in the upcoming sessions. So you just select these parameters for the bare structure in a job control. Here you give the name supercell all properties. So this will compute a single point energy for the supercell and will also compute different electronic properties, which we will discuss later. Run the simulation. So this simulation also completed successfully. Okay, close all these files. Now you can plot different electronic properties for this bare structure, like molecular electrostatic potential map, band structure, density of state, etc. So we will plot all these from this file. So select this file, right click, go to display style and remove the reciprocal. You can zoom out the structure. With trackpad you can easily move the structure from one place to another, and with the right click and on the center of trackpad you can easily rotate its axis. So this is the output structure. You can, if you do not want to show this crystal boundary, so right click on the display style, go to the lattice and now select the norm. So then you will show that the crystal boundaries disappear from the structure. So this is the output geometry of electronic properties of 2x2+1 supercell. So for plotting different sort of electronic properties, you can move to DMOL code and click on analysis. So I am going to plot a band structure plot. So click on the band structure, select the unit electron volt. You can also plot density of state plot combined with the band structure, and if you are not instructed to plot combinedly, so don't select the density of state. So click on view, you will show the band structure. This is the band gap 4.175 electron volt, a wide band gap material. So from the band gap we can easily understand that this structure will be not good for the catalytic activity. So this is the band structure. I will show you in the later lecture that how to plot this band structure and origin are in Excel. So then in the coming session we will plot this structure, because this is not so beautiful. So we will plot this structure in the origin, or we will plot this structure in the Excel for the high quality image for manuscript. So close this band structure plot, select this geometry, move to DMOL code, click analysis, and then select density of state, select full density of state. You will see this is also show a wide band gap. Here These are the home orbitals and these are the low orbitals. So we will also plot this total density state plot in the Excel or in Origin in our upcoming sessions. So you can easily extract the density of state using this method. After that, the most important thing to understand its surface charges. For this, we will plot the molecular electrostatic potential map, which will show us that which uh, site is more electronegative and which site is more electropositive. This is a graphical representation. So move to analysis, select electron density, click here and then M4. This will show you electron density plot. So now we will convert this to molecular electrostatic potential map. So sit to this view site, right click on, go to display style, and then select the iso surface and select here total electron density, and the value will be 0.2. So this structure not showing us that which point is electronegative and that which site is more electropositive. So now we will plot a molecular electrostatic potential map over electron density plot. So again, go to DMOL code, select analysis, and properties, you select the potential, click here and plot the structure. You will see such sort of structure. So right click, display style, go to isosurface, then select electrostatic potential map and select the value 0.2. Set this value to 0.2. So this is molecular electrostatic potential map, but this is not clear because the electron density plot are combined with this. So select the plot showing below the molecular electrostatic potential, this blue plot. Select here, click, this will be selected, so click and delete this. Now this is the clear molecular electrostatic potential map. You can change the color from right click, color map. This is a reverse rainbow. We are mostly using rainbow. So in rainbow color, the blue spot showing the most electropositive region, the red spot showing the most electronegative regions, the green are the less electropositive, the yellow are less electronegative, while the other green are showing neutral sides. Blue for electropositive, red for electronegative. So we are interested in the red and blue spot. So this showing the high electron density over the negative electron density over the nitrogen atom, and high electropositivity over the boron atom. You can change the quality of this plot. Bands, convert these bands to 128, so the resolution will be more clear. Show legend, the color of value will be black. You can change the size of bonds and also its style, if and also the size of legend. This shows the most electronegative region and this shows the most electropositive. Then we will copy paste these structure to PowerPoint, and I will show you in the later sessions that how to set these plot in the PowerPoint for the manuscript. So this is the molecular electrostatic potential map. Right click, display style, you can change its view. Go to isosurface. If you want to transparent this structure, so increase the transparency, so you will then show the structure below the molecular electrostatic potential, which will help the audience to easily understand that which site is electropositive and which one is electropositive. So this is the molecular electrostatic potential map. On behalf of this plot, we will select that how interact the targeted gas with this surface. As we know that into um, molecule has three atoms, two nitrogen, one is oxygen. And nitrogen and oxygens are electronegative. So with the help of this plot, we will interact the oxygen or nitrogen side up into with the positive side of this, which I will show in the upcoming lecture. Thank you. If you have any question, please put your questions in the group. Uh, then we will discuss why we are using different parameters, why I select this structure. So such type of question, if there are in your mind, so please ask me. So next, this is the structure I use here is periodic structure. You can also use a non-periodic structure for such type of simulation. I will show you in the upcoming session that how to use the non-periodic structure for such type of simulation, and what is the difference between the periodic and non-periodic. I will discuss this in the later lecture. Thank you.